Lastana
Hello, Professor Satish Kumar. Hello, sir.
ആണോ ഒരു കാര്യം ചെയ്യും ഇവിടെ നിന്ന് സംസാരിച്ചു ഇവിടെ സംസാരിക്കാൻ സാറെന്തോ വിളിച്ച പോലെ മാറിയോ അയ്യോ അത് മാറി കേട്ടോ ഇല്ല ഈ പാർട്ടിസിപ്പൻസ് അല്ലേ ഇപ്പൊ പാർട്ടിസിപ്പൻസ് എല്ലാം കയറി. പാർട്ടിസിപ്പൻസ് കുറച്ച് പേര്: ധനുശ്രീ, തനുജ, ഹരിപ്രിയ, ജിജി ജോസ്, സത്യനാരായണ. PRC സതീഷ്. PRC സതീഷ്.
Hello. Madam, sir. Hello.
Hello, Professor.
Hello, professor. Hello, professor.
Hello, Professor Satish Kumar. Loganathan.
Good evening, professor. Good evening.
Good evening. Good evening.
Good evening, sir.
Good evening, sir.
Good evening, madam.
Namaskar.
Good evening, madam.
Good evening, sir.
Loganathan.
Yes, Manu here, sir.
Happy to join with you to this event.
Yeah. I got confused with the dates yesterday and I thought it was on 4th and 5th. And I logged in yesterday and nobody was logging in. Then I rang up Dr. Shubha.
Okay.
Any special instructions for us, sir?
We are given with that
Format.
the abstracts
Yeah.
and the schedule. So today we have 9 papers. Tomorrow we have 9 papers. 9 candidates presentations. And the pro forma they have given.
Yes.
The time they mentioned 15 minutes for presentation, 5 minutes for discussion. It is an interesting exercise they are giving us.
Pardon, sir?
It is an interesting exercise.
Yes, yeah. I will just check that format once again.
Yes.
Hello, professor. Can you hear me?
Yes, Professor.
Welcome, professor. Welcome.
Thank you. Good evening.
Good evening, professor. I have a meeting at Kerala Public Service Commission.
Oh,
Why? And rush to here and then initiated. That's why.
congratulations for this consistent efforts.
Thank you, Professor. Thank you. And in between, I am sending a reminder to all. That's why.
Yeah, sure. We received the mail, and Professor Subha Madam, she has been consistently in touching with us.
Oh, okay.
And you have been giving instructions.
Yeah.
I mean, you have been giving details, updating details as and when this is ready.
Yeah. I also have the copy. No problem. It was very good. In fact, your support is very valuable to us.
It is our pleasure to join you in this knowledge-based exercise.
How is the Central University professor? Yeah.
Yes, of course. As usual, we do our teaching and research work, and they keep us very busy.
Oh, okay.
So, somehow or other, we are tightly engaged.
Oh, okay, professor.
Things are quite interesting.
Very good.
Still, we have many
Yeah.
distance to go. Many things are there. We have to do it.
Oh, okay.
And Professor Vijayalakshmi is our head of the department.
Yeah. He called me some time back, and she will also join with us in between.
Yeah.
Okay. Now the time, 5:15. Shiva teacher.
Yeah, good morning, sir. Good morning, dear professors. Sir, I won't be able to on the video because I'm traveling, sir.
What happened?
I'm traveling, so I won't be able to on the video. I hope it is okay, sir.
Oh, don't worry.
So, good evening. So, shall we? I hope all the contestants have joined.
Our jury members and initiate the program.
Of course,
Good evening, Professor Satish Kumar.
Good evening, madam. Good evening.
Good evening.
What about Professor Ghosh also joined?
Professor D.K. Ghosh, I think he's yet to join.
Okay.
Yeah, I should I call her, sir? Call him, sir, because I don't know whether he has seen the new link. Should I give him a call? Or...
Better, madam.
Yeah, because the link has changed. 1 second, I'll just give him a call and see.
Dr. Satish, namaskar. This is Dr. Prasad. Dr. Satish, namaskar.
Okay. Yeah. Namaskar, Professor.
Namaskar. How are you? All is well?
Fine.
Okay. Great.
Yeah.
Watching you after a long time.
Very good.
Thank you, sir. Thank you. My regards to everyone in the group.
So your support also be valuable to us. Yeah.
Yes.
Professor Ghosh is not picking the phone, sir. So what should we do?
Hello, teacher.
Satish, sir?
Don't get worried because we have a few more minutes. In between, I hope
No, sir.
Professor sir, can initiate the if possible, try to take 1 or 2 minutes by the time. One second, the respond actually.
Yeah, okay. The phone is ringing, but it is not getting picked.
But, no. So I got a Professor Ghosh. He will join soon.
Okay, okay.
മറ്റേതിന്റെ ഇതാണ് അതുകൂടെ എനിക്ക് ഷെയർ ചെയ്ത് യൂട്യൂബ് ഹലോ പ്രൊഫസർ Mone. Hi, Professor. Hi, welcome. Hi.
Yeah. Good evening, Professor.
Teacher, please start.
Okay,
Now,
okay.
please invite.
So, good evening, dear professors and dear participants and other members who have joined the meet. We have entered the final evaluation round for the Best Paper Awards, which are instituted as part of ICSTC 2024. These awards had been this competition has been conducted for the past 10 years, and this is the 10th final session that we are handling in association with ICSTC. So this year we have got 18 participants to compete for the 6 awards, and we have got a wonderful jury committee headed by Professor Loknathan sir to evaluate the papers. Say about the awards, these awards, there are 6 awards that are being given away today, and these awards were instituted in the respectful memory of the great professors of statistics of the University of Kerala. The awards are Professor U.S. Nair Best Paper Award, Professor Eliama George Best Paper Award, Professor R. Krishnapillai Best Paper Award, Professor P.S.J. Nair Best Paper Award, Professor Jacob Sundarraja Best Paper Award, and Professor R.N. Pillai Best Paper Presentation Awards. So, regarding the participants of today's competition, they were shortlisted from nearly 100 participants who had competed in the initial first round of ICSTC during our conference, 3-day conference conducted in December 2024. They were shortlisted, and they'll be presenting the same papers that they had done during December. Regarding the jury members, the jury convener is Professor Loganathan A., who is a professor in the Manonmaniam Sundarar University and now currently working with Central University. He has been a well-wisher of the University of Kerala as well as ICSTC, and he had been along with us for the past so many years, always willing to be there whenever we needed his cooperation and help. Then we have Professor K.S. Bhanu, who is a retired head, Department of Statistics, Institute of Science, Nagpur. Regarding ma'am, she has also been a continuous supporter of our initiatives. And we have Dr. D.K. Ghosh, the professor, Department of Statistics, Saurashtra University. So three eminent jury members are present with us, and they'll be judging the participants on their on various factors, including their content, the way of presentation, their ease of handling the subject, and the timing in which they'll be completing their presentation. Regarding timing, each participant will get 15 minutes of presentation, followed by 5 minutes of discussion. So that is a format of today's paper presentation competition. Now I'd like to welcome our dear Professor C. Satish sir, who is the brain and heart behind this whole program, to please say a few introductory words and welcome the dear jury members. Satish sir, over to you.
Welcome all the jury members, great professors, Professor Loganan sir, Professor D.K. Koch, and Professor K.S. Banger. I'm not taking more time. Let us start the
Yeah.
program.
Yes.
Jury members, do you want to say anything? Now it is given to you, all the convener, Professor Loganan sir, and other professors, Professor D.K. Koch and Professor Banu, for other proceedings. I'm not taking more time because now it is 5:30. You can take
Yeah.
your
So
line.
Lognathan sir, please.
Yes, madam.
Thank you.
Well, good evening to all. Thank you, Professor Satish Kumar and Dr. Subha, for giving us this opportunity to attend the presentations to be made by the youngsters for the awards. And we are going to hear new topics also. So it is a benefit, besides being a jury, it is a benefit to us to hear the new topics and new results. And thank you. On behalf of the committee of juries, we thank Professor Satish Kumar and Dr. Subha and the team for giving us this opportunity. Uh, uh, Good evening, Professor Banu, Professor D.K. Ghosh, to be in the same committee for evaluating the paper presentations for the award of six important awards established in the names of the great professors. Sir, as they have given us some instructions regarding the time duration for each presentations, there are nine papers scheduled today and nine other papers are scheduled tomorrow. For today there are nine papers. Each paper presentation is given with 15 minutes for presentation and 5 minutes for discussions. So now itself already the time is 5:32. Professor D.K. Ghosh, Professor Banu, do you want to say anything as instructions to the presenters, please?
No, sir, you have spoken on behalf of us. I think we can start.
Sir,
Thank
can
you
I
very much,
add
sir.
1 second? Lognathan sir, 1 second, sir.
Madam?
Actually, three of the presenters hasn't. Dr. Deboy Thakur has sent a message that he won't be participating. Deboy Thakur. Then Tirunavukarasu and Dr. Rohin Mishra hasn't replied yet. So
Okay.
please take that, note that, sir. Thank you.
Okay, well. So, as far as today is concerned, Professor D.K. Ghosh and Professor Banu, shall we check with the availability of the presenters? Well,
Sir,
Gigi Jo,
unmute.
G-
Yes, present, sir.
Gigi Jose is Dr.
Thank you, Professor Satish Kumar. You gave me this opportunity to evaluate the best paper awards. I've gone through the candidates. They were from all over the India, I found, and the topics were really very interesting topics. And so I appreciate and I congratulate you that you have selected and sorted the very good papers for this award. Thank you very much.
Thank you.
Um,
Thank you, process. Let
Thank
us.
Dr. Jabir of University of Calicut, not joined. Dr. Banat Virana.
Yes, sir. I'm here, sir.
So you have joined under the name Viru Sukya, right?
Yes, yes, sir.
Dr. Shamshadur Razul. Not joined so far.
Yes, sir.
You have joined.
Yes, sir.
Well, as Dr. Subha mentioned, Tirunavakar has not joined. Tirunavakar, so no. Dr. Adil Ahmed Mir. Dr. Adil Ahmed Mir.
Yes, sir, I'm present.
Oh, you are. Dejoy Thakur, he has not reported. And Dr. Vijayalakshmi. Dr. Vijayalakshmi.
Research scholar, sir.
Well, all right. Dr. Dhanisri Tanuja.
Yes, sir. Present, sir.
Well, okay, right. Sir, Madam Dr. Manu, Dr. Digego, shall we call the first presenter, Dr. Gigi Jose, to make his presentation?
Yes, sir.
To start his presentation?
Yes,
Okay,
sir.
please call.
In fact, as per schedule, we should have started the first presentation by 5:30 evening. Now it is 5:35, so we can give him time 15 minutes. Dr. Gigi Jose, take care that you have to present for 15 minutes, and there shall be 5 minutes for presentation. Strictly adhere to the timing.
Okay, sir. Am I
Join.
audible?
Yeah, you're audible.
Audible. Show your face and make presentations.
So my screen is visible.
Yeah.
Yes, your screen is visible.
Good evening, everyone. I am Gigi Jose, research scholar, doing research under the guidance of Dr. K. Jayaguma, Senior Professor, Department of Statistics, University of Calicut. The topic of my presentation is an infinitely divisible distribution on non-negative integers with application to the medical data. This is the overview of my presentation. First, introduction. In many practical problems related to engineering, medical science, any other applied sciences, the count data phenomenon are often interest, such as the number of earthquakes occurring in a calendar year, the number of accidents at a specific location, the frequency of an individual visits to a doctor, or the number of claims faced by an insurance company. So the need of discrete distributions increases day by day for capture the diverse features of the real data set, such as the degree of asymmetry, their under or over dispersion, or the different shapes of their failure rate function. There are many methods for developing the discrete distributions available in the literature. For example, adding parameter to the existing discrete distribution or compounding method. Other one of the method is the discretization, discrete analogous of continuous probability distribution. One method is the survival discretization. Several discrete distributions are proposed through the survival discretization, such as discrete variable by Nagbaga and Osaki in 1975, discrete variable geometric distribution Jayagumar and Babu in 2018, discrete new generalized Pareto distribution by Jayagumar and Jose 2022, and discrete exponential independent Poisson distribution by Jayagumar and Jose 2024. Mainly, the Pareto distribution is one of the widely recognized continuous distribution having the heavy-tailed property, which have applications on financial and insurance data, but it does not provide a reasonable fit for many applications. For example, the number of claims per policy holder can follow a discrete heavy-tailed distribution. So the need of discrete heavy-tailed distribution is needed very much in the for applying the real data sets. Some few discrete heavy-tailed distributions are listed in the literature. They are discrete Barr and discrete Pareto distribution developed by Krishna and Pundir in the have applications in biological data sets, and Pareto et al. Proposed discrete generalized Pareto distributions which have applied on modeling raw data sets. And Parangene 2016 introduced discrete 3-parameter Barr type and discrete low mass distribution, and Ghosh in 2024 developed the discrete Pareto type 4 distribution. Here we introduce a new discrete distributions which generalizes discrete Pareto distribution. The cumulative distribution function of the proposed distribution is given here with the parameter A, B, alpha and beta which is greater than 0. Now we look how the proposed model is developed. Jagumar and Jones 2025 proposed a discrete low mass generator with PMF given in equation number 2, and alpha and beta belongs to 0 and infinite. We putting the CDF of Weibull distribution in equation 2, we got the PMF of the generalized discrete Pareto distribution given here. Then this new distribution can be considered as an alternative to discrete bar, discrete Pareto, and discrete generalized Pareto distributions. The distribution is not only over-dispersed and zero-inflated, but also infinitely divisible. And the distribution is unimodal with in zero vertex and have a common Poisson representations. The main motivation for developing this lifetime model are to propose a new generalized version of the discrete Pareto that can be used particularly to analyze medical data and in the study of reliability problems, to model count data with heavy tails, to consistently outperform other existing discrete Pareto distribution as well as other widely recognized discrete distribution mentioned in the literature. Look at the distributional properties. The PMF is given in equation 3, and we denoted the GDP distribution as GDP A, B, alpha, and beta. Now, also, we can rewritten the PMF given in equation 3 as 4, where B in between 0 and 1, B is equal to exponential of minus alpha. These are the special cases of generalized discrete Pareto distribution. One is discrete Burr distribution, discrete Pareto distribution, alternate discrete Pareto distribution, discrete generalized Pareto distribution, and discrete Pareto type 4 distribution. This is the limiting behavior of the generalized discrete Pareto distribution in aspects of the parametric choices. At A tends to 0 or infinite, the PMF tends to 0, and B tends to 0 or infinite, the PMF tends to 0. As B tends to 0, the PMF becomes 0, and beta tends to infinity, the PMF becomes infinite. As n tends to infinite, f of t plus n by 1 minus f of n is equal to 1, which implies the generalized discrete Pareto is a long tail distribution. Also, n tends to infinite, probability of n greater than n by n raised to minus alpha, which is finite, which implies GDP is heavy tailed distribution. The PMF presented in equation 3 is log convex. As a direct consequence, GDP distribution is infinitely divisible. For more details, see Stutel and Manhunt 2004. Moreover, as any infinite divisible distribution defined on non-negative integers has a compound Poisson representation. So the GDP distribution have compound Poisson representation, and the maximal limit for the variance in case of the infinitely divisible distribution is represented here. These are the plots for the probability mass function. From these plots, we clear that the PMF is always decreasing and have a unimodal at the zero vertex. Then the moment properties, we establish the bound for the moments, and the rth moment will be convergent if alpha be greater than r. We can derive a theorem like expectation of n raised to r exists if and only if exponential of r by b, which is greater than b. These are the mean variance given as kurtosis for the various values of the parameter choices. From this table, it is clear the variance is always greater than the mean. So the GDP can be better for modeling over dispersed data sets. When we look at the hazard rate function is given here in equation 5 and the reverse hazard rate in equation 6. The hazard rate and reverse hazard rate function of the GDP distribution is always decreasing. The cumulative hazard rate function in equation 7 and the corresponding alternative hazard rate function in 8. We found a result. The alternative hazard rate function represented in equation 8 uniquely determines the GDP distribution. These are the failure rate plots of the GDP distribution for the various values of A, B, B, and beta. From it's clear that the GDP have decreasing hazard rate function. When we propose some stochastic ordering of the GDP distributions, let N1 follow GDP A1, B, B, beta, and N2 follows GDP A2, B, B, beta. If A1 greater than A2, then N2 is stochastically larger than N1. If B1 greater than B2, then N2 is stochastically larger than N1. If B1 greater than B2, then N1 is stochastically larger than N2. And if beta 1 greater than beta 2, then N1 is stochastically larger than N2. And the corresponding expectational hazard rate ordering is given here. Then the discrete aging intensity and discrete alternative aging intensity as given in equation 9 and 10. If for a discrete random variable n, discrete aging intensity L has the form in equation 9, which have then n follows GDP distribution. The odds ratio given in 11 and 12, both Wn and W bar n presented in equation 11 and 12 uniquely determines the GDP distribution. Then we move to the characterizations. First characterization is based on the conditional expectation of the certain function of the random variable if n follows GDP a, b, v, beta if and only if the expression is given in 13. And next is based on the hazard rate function. If n follows GDP a, b, v, beta if and only if hazard rate function satisfies the different equations in equation 14 with the boundary condition h of 0 is equal to b raised to log of 1 plus a raised to b by beta minus 1. And this is based on the reverse hazard rate function. If n follows GDP a, b, v, beta, if and only if its reverse hazard rate function satisfies the difference equation in equation 15 with boundary condition star of 0 is equal to 1. To study the extreme cases of the parameter when a, alpha, and beta become either in 0 or infinite, we introduce an alternative parameterization of the GDP distribution. Here we take b is equal to 1 and the new parameter is defined as lambda is equal to 1 by alpha and theta is equal to 1 minus e raised to minus a by lambda beta, and the corresponding PMF of the GDP takes the form given in equation 16 and lambda, the parameter lambda greater than 0 and theta in between 0 and 1. Through the alternative parameterization, we propose some propositions. Let n follow GDP lambda theta distribution. The parameter alpha tends to 0, then n converges in distribution to the geometric random variable. Also the lemma, let k belongs to n naught and theta belongs to 0 and 1. The limit lambda tends to infinite. Log of 1 minus lambda k log of 1 minus theta by lambda is equal to 0. And another proposition, suppose that y has a gamma distribution with shape parameter 1 by lambda and scale parameter gamma here, and the PDF of y is given here, and the conditional distribution of t given y has a geometric distribution with parameter 1 minus e raised to minus y, then t follows GDP lambda theta. This is the relationship between gamma distribution. And some theorems as established related to the GDP distribution. First one, let Z is equal to minimum of Ni, and Ni's are non-negative IID integer value random variable. Then Z follows GDP AB B raised to M beta if and only if Ni follows GDP AB V beta. This is a property which is closure under minimum, and it can applications in reliability modeling of series system. Another theorem, if Ni's be non-negative IID integer valued random variables and Z is equal to minimum of Ni, then Z is GDP A, B, V beta if Ni's are GDP A, B, Vi beta, where V is equal to product of Vi. And another one is if N is a non-negative integer value random variable and S is a positive number, then N raised to S follows GDP A, B by S, B beta if Na follows GDP A, B, V beta. Another theorem, n follows GDP A, B, B beta, then Z is equal to log of A raised to B by beta, N raised to B
Dr.
plus.
Jijijos, you have
Yes,
3 more minutes. You have 3 more minutes.
Okay, okay.
You have only 3 minutes.
Okay. It follows geometric distribution, and another two theorems are established here. When the Conde function is given in equation 17 and the particular median is given here, we can generate the random variable using inverse transformation method using the equation 17. Then the estimation method, the log likelihood function is given here, and the likelihood functions which are not closed. So we use some numerical techniques for finding the estimate. Here I employ R programming. These are my simulation steps. I obtain the MLE value bias, mean square error, absolute bias, and mean relative error for the various choice of the parameter. From these tables, it is clear that the parameters values approaches to the estimates of the values approaches to the parameter, and bias and mean square error and ABBB and MRE decreases as the sample size increases. Next, the numerical examples. Here we taken the number of wards observed from the ward treatment of 90 patients using immunotherapy. The data having over-dispersion properties, and we compare the distributions with discrete Pareto type 4, discrete Bartol, and discrete additive Peirce variable distributions. The data set is given here, and the fitting is here. From these tables, it is clear GDP having highest p-value and lowest local AIC, BIC, AIC, HQIC, and KS values. Some conclusions. Here we introduce a new discrete distribution, which is an alternative to discrete Pareto, and various properties of the GDP distributions are studied. It is a competitive model with other existing Pareto
Hello, sir.
models.
Hello.
And the model have decreasing failure rate and is suitable for over-dispersed data set. And also as a
Hello.
limitation, considering that the hazard rate function of the GDP distribution decrease for modeling real-world scenario with increasing and
Hello.
Bartlett-shaped hazard rate, we are unable to
Hello.
apply these distributions. So this facilitates the developments of better adapted versions of the discrete Pareto models. These are my references. Thank you.
Congratulations, you are on time. Well, now the session is open for questions. We have 5 minutes for interaction with Gigi Jose, Professor Banu, Professor DK Ghosh. Please, if you have any questions, ask.
Gigi Jose, what I found that Pareto distribution is generally used for the income distribution.
Yes, sir.
So, in your trial, there is no case of anything about the income. Simply, you are taking a distribution and you are solving it. Median, variance, etc. Kurtosis, BIC, IC. This is first question. Why it is that? Second question, you are saying we have taken the 4 parameters A, B, B, and beta. And with different value of alpha, beta, A, and B, you are showing these some distributions are particular case of your distribution. If all the distribution are particular case of your distribution, then what is necessary of bringing this distribution? And third question is that you have taken another parameter lambda, saying lambda is equal to 1 by alpha A. So when again, if you put that model, that lambda, still instead of A, still you have the 4 parameters. So with 4 unknown parameters you are estimating. So what is need of the lambda? But same your alpha you are estimating. And after estimated alpha, you can find out the lambda. This is my 3 questions.
The first one, Pareto distribution is mainly for the income aspects, but in literature, so many few discrete distributions are developed. These distribution as application in many fields, such epidemiological area, reliability area, medical area.
This is generalized. This is generalized. A particular case you can say this is generalized. This is generalized. This is not the truth.
Already developed the models, discrete distribution by Krishna and Kumar. These have applications in the biological field, and the discrete generalized Pareto distribution proposed by the Plato et al. Application for fraud access data. So, in the case of discrete aspects, we need more count data distribution for modeling such data sets. So, we propose these type of distribution for modeling count data phenomena. In my distribution, I taken the medical data having a better fit when compared with existing discrete Pareto and other 4 parameter distribution. Next question.
All distributions are particular case of your distribution for different value of A, B, V, and beta.
Sorry, sir.
All other distribution are the particular
Special cases of my distribution.
Yeah.
Special cases of my distribution.
That
Means my distribution generalizes. Yes, sir.
What is need of when all distributions are available? What is need of new distribution?
This is a generalized version of the existing Pareto distribution, sir. This is a generalized version. Generalization of the existing Pareto model.
But that you have not said anywhere. Anyhow, but it means this is completely theoretical. There is no application so far.
So my distributions have applications in all the existing Pareto model behaves.
Okay.
Well, Dr. Banu.
Dr. Gigi, good presentation. Dr. Ghosh has already asked you many questions. I was also going to ask you about the application point because your theory, your title itself says it's an application to medical data.
Yes. So I take only one data from the medical aspects. It's taken from the dermatology parts.
And you find that this distribution fits very well
Yes.
compared to the others.
Other existing Pareto and one for parameter existing distribution.
Okay. Okay.
Well, thank you.
Thank you.
We have only one more minute to discuss with Dr. Gigi Jose. So let me take this. What is the motivation for taking up this distribution for your study?
Uh, I already mentioned a
You know,
few.
as Professor D.K. Ghosh has mentioned, and you mentioned that there are several distributions, and you have developed a distribution which is a generalized version of all other existing distributions. What is the motivation for taking
Yes,
up this one?
it's a generalized versions of the all existing Pareto distributions are. Only few discrete Pareto distributions are developed. This is the generalized version of the existing four discrete Pareto distribution. Not all the existing discrete distribution. It is only the generalized version of the discrete Pareto models. Existing
No,
discrete Pareto
Okay,
models.
time is over.
well, okay, right. Thank you, Dr. Gigi Sos. Let us invite the next presenter, Jabir, Dr. Jabir.
Hello, sir. Is it
Yes,
audible?
yes, audible. Show your face in the camera and start presentation.
Okay. Is it visible, sir?
You are visible. Please show your
Okay.
screen.
Show your presentation. Don't delay it.
My name is Jabir. I am a PhD research scholar. I am doing PhD under the guidance of Dr. Bindu PP, Government Arts and Science College, Calicut. My topic of presentation is the Harris Extended Diagonal Distribution Theory, Properties and Applications. These are the brief outline of my presentation. Introduction. The diagonal distribution was proposed by Diagram in 1977. It is an alternative to the Pareto and log normal model for modeling personal income. It has a wide range of applications, including income and wealth statistics, metrology, and reliability and survival analysis. A continuous random variable X has a three-parameter diagonal distribution. Its PDF is given equation number 1, and its survival function is given equation number 2. In probability theory, it is common to practice to modify existing probability distribution to make them more flexible. This can be done by adding more parameters, transforming the original distribution, or combining two distributions with suitable mixtures, among other methods. Alley and Beckhoff in 2011 recently proposed a convenient method for adding two parameters to a baseline distribution, which provide more flexibility for modeling various types of data. This novel approach is based on the probability generating function of a discrete distribution introduced by Harris in 1948. Pesticides and Lamonde in 2015 considered the Harris extended family of distribution with respect to some lifetime models. Since this method is based on the probability generating function introduced by Harris, the resulting family of distribution is known as Harris generalized family of distribution. This generalized family includes Harris extended exponential proposed by Sinha et al. in 2015, Harris Lennox distribution introduced by Ogunda et al. in 2021, and Harris extended two parameter linear distribution developed by Thomas et al. in 2001, etc. The reliability test plan based on these families is also in the literature, such as Jose and Cole in 2018 derived reliability test plan for percentage based on Harris generalized linear exponential distribution. Jose et al. in 2018 developed a reliability test plan for Harris extended variable distribution, etc. The motivation behind this research is to develop a new lifetime distribution called Harris Extended Diagonal Distribution using Harris generator. This new model adds flexibility to the original diagonal distribution and allow for a wide range of shape, its density and hazard rate function, making it more adaptable than some existing generalization. The Harris extended family of distribution is defined as follows. If g bar of x and g of x and rg of x represent the survival function, PDF and hazard rate function, so then survival function of Harris section family is given equation number 3, and PDF is equation number 4, and the hazard rate function is given equation number 5. Now we define the new distribution. We propose the our distribution had a suspended diagonal distribution based on the equation number 3 and 4. Then the PDF of the proposed distribution is given equation number 6, and the CDF of the proposed model is given equation number 7. And this is the PDF plot for the proposed distribution for different parameter values. From this plot, we can identify that the distribution shape is decreasing and unimodal. In some parameter value, it's flat. It is right skewed and left skewed, and some parameter combination is symmetric as well. Now we discuss the reliability measures. Hello.
Yes, we can hear you.
You are audible.
Oh,
Continue. You are audible.
Okay. Reliability measures. The survival function of the proposed model is given equation number 8, and the hazard rate function of the proposed model is given equation number, and the cumulative hazard function is given equation number 10, and the reverse hazard rate function is given equation number 11, and the odd function is given equation number 12. This is the plot of the hazard rate function, plot of the proposed distribution. From this plot, we can identify that the hazard rate is decreasing and UBT parameter values. Now we are given the expansion for the PDF and CDF function. Let g of x is equal to alpha into g of x into g bar of x raised to alpha minus 1 be the exponential density function with power parameter alpha greater than 0. We demonstrate that the PDF can be expressed as a linear combination of exponential densities. There are two cases. When case 1, when lambda is less than 1, we consider the negative binomial series and complete gamma function. We can write the equation 6 as equation number 13, and when the lambda greater than 1, the equation 6 can be written like this, equation number 14. And combining two expression, we have equation number 15, where tau jc plus 1 of x is given here, and also wj is given equation number 60. Now, by applying g bar d of x and gd of x in equation number 14 and simplify, we get equation number 70, where pij of s is given here. Now we are moving to the expansion for the CDF. By using the generalized binomial series expansion for lambda less than 1, we can write the CDF of the proposed distribution like this, equation number 18, in the case of lambda less than 1. If the lambda greater than 1, this equation can be written like equation number 90. And combining two expressions, we can write like equation number 20. Now we are moving to the moments and associated measures. The first one is characteristic function. By using the definition of the characteristic function, the proposed distribution can be written like equation number 22. Now we make a substitution 1 plus alpha x raised to minus theta all raised to minus 1 equal to u. Then, and we are applying its limit, we get equation number 23. Now we using the expansion of e raised to tx, we can reduce the above model like equation number 24. And finally, we get the characteristic function is given equation number 25. Now we are moving to rth non-central moments. The rth non-central moments of the proposed distribution can be written as equation number 26. Now we make a substitution 1 plus alpha x raised to minus theta all raised to minus 1 is equal to u. And proceeding the same, we get the equation number 27, and finally we get the rth non-central moment is given here. And if we are finding the first four moment, if we are putting r equal to 1, 2, 3, and 4, we get the first four moment, which is given equation number 31, 32, and 33, and 34. And we are also calculate the variance of the proposed distribution, which is given equation number 35. Now we are moving to the moment generating function of the proposed model. The MGF of the proposed model is given equation number 37, and also condates The quantile function of the proposed model is written in equation number 38. Now, also we can calculate the lower quartile and the median and upper quartile of the proposed model by substituting 0.25, 0.5, and 0.75. And also we can calculate the median, which is given equation number 39. Now, by using Galton's skewness and more kurtosis, by using this formula, we can calculate the skewness and kurtosis of the proposed model. And this is the numerical illustration of the proposed model, proposed the skewness and kurtosis of the proposed model. Here we are fixing alpha, beta, theta. From the table, we are fixing alpha, beta, theta, lambda is equal to 0.5, and varying the values of t, we get the skewness and kurtosis values. From this, we can observe that the kurtosis is increasing and the skewness is leftly skewed. And similarly, alpha, beta, theta, and C are fixing 0.5, and we are varying the values of lambda. We get the skewness and kurtosis value. From this, we can observe that the kurtosis is increasing. That means we are tight, and it is from the positive skewness to the negative skewness. And also similarly, we are fixing alpha, theta, lambda, C as equal to 0.5, and varying the values of beta, we get the skewness and kurtosis value. Similarly, if we are fixing the beta, theta, lambda, C is equal to 0.5, and we are giving the various values of alpha, which are shown here. Similarly, in the case of theta is varying, and also fixing the remaining values we get here. And also we are plotted the 3D plot of the proposed distribution, which is shown here. Now we are calculating the mean deviation about the mean and median. The mean deviation about the mean and median is obtained by using the formula 42 and 43. By using the relation 44 and 45, we can easily find out the median of the proposed mean deviation about the mean and median deviation about the median of the proposed model, which is given equation number 46 and 47. Now we are calculated the order statistics of the proposed model. The PDF of the kth order statistics can be written equation number 48 by using the generalized binomial series expansion and power series expansion and simplification. We get equation number 49, where phi s comma q is given equation number 50. Now we are moving to the uncertainty measures of the proposal model. Here we are calculating different types of entropy measures such as Rainy, Arimoto, etc. The first one is Rainy entropy. Rainy entropy is obtained by using equation number 51, and we are using a substitution u equal to 1 plus alpha x raised to minus theta whole raised to minus 1. Finally, we get the Rainy entropy is in equation number 57. Based on the 57, we can easily derive other entropy measures such as Callis entropies, which is given equation number 59, Arvara and Serval entropies, which is given equation number 60, and the exponential entropy is given here 62. And
we have 3 more minutes, only 3 minutes.
Okay, delta entropy is given at 64, and the extropy is given 65, etc. Inequality measures, we are calculating the Bonfranc and Lorentz measures of inequality. The Lorentz measure is given equation number 71, and the Bonfranc measure is given equation number 73. And here we are using the method of maximal likelihood estimation. The likelihood function is given equation number 47. The log likelihood function is given equation number 75, and the different log likelihood equations are given 76 and 77 and 78 and 79 and 80. These MLE are nonlinear equations. We can solving them iteratively using Newton-Raphson method in R. The asymptotic distributions of the proposal model is also derived. Now we are going to the simulation study. Here we are conducted a simulation study of the proposed model for the set of parameters values, which is given here. And here to generate the random number, we are used inverse transformation method. and for the various sample size 10, 50, 100, and 200. Each experiment was repeated 10,000 times. And from this table, here we are given the tables of the simulation result. From this table, we can identify that absolute bias and mean square error is decreasing in the both the table. So we can say that the model is best. And the application of the real data set, the proposed Harris Rankin distribution is applied to real data set to the acceptability of the new model. We are comparing our model to the other competing models such as the Rankin distribution, Burr distribution, and generalized inverse Kumaraswamy distribution, inverted Kumaraswamy distribution, and exponential inverted Kumaraswamy distribution, generalized inverted Linley, and exponential inverted Linley, and inverted modified Linley. And we are calculated the AIC, CIC, DIC, HQS, KS, and P values. For this, we are consider the data set for the monthly remission time of 128 patients with bladder cancer data, which was given B and 1 in 2003. This is the information criterion for the bladder cancer patient data. From this, we can identify that the our proposed model has lowest AIC, CIC, CPSC, DIC values. And similarly, we are finding the KS test values and the P value. From this table, we can identify that our model has higher P values, that is 0.99. So we can easily conclude that our model is best compared to other competing models. Also, sir,
No. Your time is over because there are several other presenters, so we have to adopt
You stop
time.
it.
Okay.
I told you
Stop it now, please.
you have only 3 minutes.
Okay, sir. So, likelihood ratios also calculated, confidence interval also calculated. The fitted PDF, CD plot are also plotted. And finally, we are concluding this paper proposed a new distribution called Harris section diamond distribution. The newly proposed more structure population applications are investigated. The proposed distributed with the maximal likelihood method, where a central distribution confidence interval is investigated. A similar study is performed where the actors of the maximum likelihood estimation. The LA test is conducted to evaluate the goodness of it. The proposed distribution led to favorable failure data set for the newly proposed Harris method, other competing models. And the proposed distribution has wide application model for decreasing failure rate and EBT failure data set, and the characters can be found in many real world data set. We can design a reliability test plan based on this proposed distribution. These are the reference. Thank you.
Okay, nice. Now the session is open for interaction. Dr. Banu, Dr. Ghosh.
Thank you, Mr. Jabir,
Thank you.
for your good talk. I have 2-3 questions. The first question is this: your distribution is left skewed distribution. This shows that in the beginning, the survival rate is more, and as the year passes, survival rate is decreasing. This is one question. You give answer why. Second question was that all the moments are less than 1.
Yes,
All moments. Is it justified for any distribution? And third case was that in some cases you are taking 3 parameter alpha, beta, and C, and somewhere you are jumping to alpha, beta, and theta. Somewhere you are jumping to alpha, beta, C, and theta. And the last question, that in one case your kurtosis was 15 point something, and all other cases it is more or less same. Is it typing mistake or it is true?
Sir, the first question, can you repeat one?
That is, your distribution is left skewed distribution.
Yes,
graph
yes.
shows. This shows that as the year passes, survival is first will be increasing, and after year passes, survival rate will be decreasing. How you can justify with your distribution? Okay, go for second question. Your all the moments are less than 1.
Yes, sir. Yes, sir.
Is it justified for any distribution and for
Yes,
application?
yes. Diagonal distributions also moment is less than 1. In all cases, or all generalization of the diagonal distribution from which moment is less than 1. It's r is theta, r is less than 1, r by theta is less than 1.
Then what is need of finding these moments when we know that all moments are less than 1? No need of finding moments or characteristic function. And third question was that,
And
of course, time is more. Let us ask some other person. Let some other person should also ask.
Dr. Banu?
Hello, Jabir.
yes, sir. Yes, madam.
You talked about flexibility of the model.
Yes.
So can you justify how your model is more flexible than the others of the similar?
Actually, the Harris family is developed for increasing the flexibility of the model.
Pardon, I'm not able to hear it.
Hello.
Excuse me, Rasul, just mute your mic. Rasul,
Not my mic.
Rasul.
Dr. Rasul, please mute your mic. We are not able to. Yeah, please, JB.
Hello, madam.
Yeah.
Actually, the Harris family is developed for to increase the flexibility of the existing model.
Yeah.
So when we are using the Harris extended family Harris generator, the baseline model should expand their flexibility and their adaptability for the real data application.
So you have just you have checked that.
Yes.
To say your model is more flexible.
Yes, I have already shown in my PPT. When we are compared to the real data application, from this we can I will give from this table we can identify that the first model is our proposed model is p-value is 0.9, and the last one is the diagonal distribution is p-value is 0.60. So the model is very flexible.
Okay, compared to the others.
Yes.
Okay, thank you.
Well, congratulations, Dr. Jabir. But however, you could have managed time because you did not give time to ask questions. Right.
Okay.
Thank you.
Okay.
Next, you close your screen. Now, next presenter, Dr. Banod Viranna.
Yes, sir. I'm here, sir.
Yes.
Visible, sir, my screen?
Yes, you are visible. Show your screens. Share your
Now
screen.
I'm, sir. I'm sharing my.
And manage your dear presenters. Please manage your time. You are given with 15 minutes for presentation, and let that be 5 minutes for interaction.
Yes, sir. Visible, sir? My screen?
Yes, visible.
Yeah. Okay, sir. I'll share full screen. First of all, thank you for Satish, sir, and committee members. And with this game, myself, Dr. Banathina. I'm doing postdoctoral research fellow at DSS SIMS, Banaras Hindu University. My topic is on bivariate pseudo logistic distribution, its properties and estimations and applications. These are the contents of my present paper. Here I introduced some two types of bivariate logistic distribution were introduced by Gumbel in 1961. One of which had is a cumulative distribution function is the equation number 1. Here the regressions curves and other key characteristics of these distributions were detected by him, and the absence of any parameter regarding the correlation between the x and y is significantly restricted the uncertainty utility of these distributions. Here we present a bivariate pseudo logistic distribution with one logistic form of form marginal density, let's say x, and the all conditional distributions of y given x is also in form of logistic distribution. So this is a definition. A two-dimensional random variable x x is a x and y is said to have a biweight logistic distribution. There exists a location parameter mu and a scale parameter sigma naught, uh, such as x follows logistic with parameter mu and sigma naught, and the function of mu of x such that y given x is follows logistic with mu of x and the set lambda 1. So here, sorry, uh, therefore, the bivariate pseudo model with the linear regression function, we assume that here the equation number 2 and 3, here mu of x is a alpha plus beta x. We put it in this place. We put it this form, linear form, and this is the parameter space. Here mu is greater than 0, greater than or equal to 0, and sigma naught is greater than 0, alpha is greater than 0, and beta is strictly greater than or equal to 0, and lambda 1 is greater than 0. So this is the equation 4 is the my joint probability density function of x and y, and here the variables x and y is belongs to real number, and this is some statistical properties, the movements of the we calculate the some movements, their movements, expectation of x and variance of x, and we calculate also conditional distribution of y given x, and their expectation of y, and variance of y also we calculated here, and also we calculate covariance and covariance matrix also, covariance also, and we also calculated correlation coefficient also. Here this is the correlation coefficient. Now we find some four cases we are there. When beta equal to 0, it follows correlation coefficient is 0. So in fact, in this case, x and y are independent random variable. So in case number 2, if lambda not equal to lambda 1, sorry, sigma not equal to sigma 1, sorry, the correlation coefficient becomes as like that. Is only depends on betas. The correlation only depends on beta. And when sigma naught equal to 1, the correlation coefficient like that. And last case is a fourth case is a sigma 1 equal to 1, then the correlation becomes this form. So here we can compute the statistical inference. First method is method of movements. This is the uh, first movement, and we simplicate that movement method of movements as a alpha, beta hat, and mu hat, and we calculate sigma naught hat and sigma 1 hat also. Then the second method is a maximum likelihood estimation for the from the equation number 4. This is the equation likelihood function, and their corresponding log likelihood function is given by equation number 5. And then we partially differentiate with respect to the corresponding parameter and equate it into 0. Then we get the following equations number 6 and 7 and 8, 9, and 10. Here, the above equations must be solved numerically to obtain the estimated parameters. That is mu hat, sigma naught hat, and alpha hat, beta hat, and sigma 1. So now we can use the fixed point iterations to find the better version of sigma naught for a given value of mu. Namely, these are the form we compute with the Newton method to find the better version of mu. So as usual, we there we calculate the likelihood ratio test. Here, the general form of the generalized likelihood test is the form of equation number 11, and here uh, uh, parameter is not is a subset of full parameter space of the evidence testing with null hypothesis. Theta is belongs to subset of parameter space. we reject the null hypothesis for the small values of t. So we construct the likelihood ratio test of the simple submodel of the following subsection. Here, uh, subsection 1 is sigma naught equal to sigma 1. The equivalent test statistics is the sigma naught equal to sigma 1. The natural parameter space under the null hypothesis of the submodel model is a parameter space not equal to. This is a after submodel we equating the sigma naught equal to sigma 1, then you the our subspace parameter space becomes to this form. Then the beside the full model of the natural form, this is the full model parameter space. So after that, under the submodel of the parameter space, the equation number 4 will becomes equation number 12. This is a log likelihood function. So now we partially differentiate with respect to corresponding parameters and equate into 0. Then we get the following equation number 13, 14, 15, and 16. Now the above equation 13 to 16 the solve numerically. Here also we solve numerically, and we get the MLE sub mu sigma 1 alpha beta. We call mu star hat and sigma 1 star hat, alpha star hat, beta star hat respectively. Now the unrestricted parameter space space that is null under the null full model, the memories for the mu sigma naught alpha beta sigma 1 are obtained from the equation number 6 to 10, and then our generalized likelihood test statistics define the equation number as will becomes to equation number 17. We put in the all parameters in the
ആരെങ്കിലും കേറിയോ നോക്കാൻ വേണ്ടി മറ്റേ ലിങ്കിൽ
our test statistics. We conclude that equation number 17.
തെറ്റിക്കൊടുത്ത ലിങ്ക്.
And the second case is sigma not equal to 1. Then we can do the same process about the submodel full subspace of the parameter space.
അങ്ങനെ
This is
ഒരു
the and then we become to the likelihood function number 18, and then similarly we partial differentiate with parameter and equal to 0. Then following equation 19, 21, 22. And here also we solve
മാളവിക
and we get the parameters. And then we all compute the generalized likelihood ratio statistics is the equation defining in the equation number 23. And next I'm going to simulation study. Because of the normal marginal and conditional structure of this model, simulating the pseudo model is very easy, very simple. And here we we straightforward simulate the approach to using linear regression for the bivariate pseudo logistic model. And we have simulated 10,000 data sets of the sample sizes n equal to 30. The sample size is 30, 50, 100, 200, and 500 up to from the following submodel and full model also. The table 1 and 2 are provide the related movements estimations and MLEs along with their bootstrapped standard errors and confidence intervals from the entire and submodels of the submodels. And it is observed that as the sample size increase, the Pearson correlation coefficients converges to population correlations, and the movement and MLEs standard errors are low. And actually, compared to the confidence interval created using movement estimation at a word confidence intervals and generated using MLE estimate has the lower length. So this is a full model of the sample, full model of the simulation study. Here mu equal to 2, sigma naught equal to 3, and alpha equal to 1, beta equal to 3, and sigma 1 equal to 2. And we compare the all PC values and with their confidence intervals and log to log L value also. And this is a simulation of model 1. Here also we take small data set. We this is the last slide. Here we
college level examination from subset X and the college qualification test CQT subset of X2 and X3 are mentioned in the Johnson's and Dixon in 2007 paper. The result is given in the table 2.5. And here the numerical method used to derive the maximal likelihood estimate of the parameters and for the Bayard pseudo logistic model. And the estimate here estimates and standard errors ASC, BSC, and PSM correlations were calculated for each full model and submodel, and they showed in the table number 3 and 4 respectively. This is the full model, and this is the submodel 1. We have developed the flexible model known as the bivariate logistic distributions by taking into the consideration the bivariate model, and in which one marginal distribution is assumed to be of the logistic form, while the conditional distributions of the second variable is given that first. I have also assumed to be of the logistic
SLR
form.
model.
And for these models, investigation has been done into the distributional and informational problems. The different bivariate logistic models that have been introduced in literature may be replaced by the models or converted to this study. The pseudo models are clear form makes it possible to fit the models and estimate the parameters easier, and as well as to simulate it simply. And however, we would contact that there extensions to the higher dimensional and permuted variational of the themselves to not a curve or these are
Is the one.
these are
Wait a minute. The likelihood estimator is the one at which the likelihood function attains its maximum.
Yeah.
Then trimming it or finding the better version, then still then your likelihood function is still further it is maximum. It means your previous estimate is not the one actual. And how good your correlation coefficient in sensitizing your distribution?
we compare to other
You were
distributions.
talking about quite often you were talking about the correlation coefficient.
Okay. Then. Yeah,
But there are other parameters, but they're not so sensitive.
no, sir.
Okay, okay, right. Keep this, and it was not mentioned in the paper.
Yes, sir.
Let Professor Ghosh and Dr. Banu give time.
My question is that what is sigma 0 and sigma 1?
These are the parameters, sir.
Now, for what?
Uh, these are the scale parameters, sir.
Hmm?
Scale parameters, sir.
Then it is a standard deviation.
No, sir. No, not a standard deviation, sir. This is like yeah, I just denoted by normal parameters, sir.
And now, since you have taken 5 parameters, mu, sigma 0, sigma 1, alpha, and beta, is it the case of the bivariate normal distribution?
Yes, this is a bivariate normal distribution. No, sir. No, sir. Sorry, sir. Normal distribution, sir. This is why I'm considering this distribution. We use one is a marginal and one is another. This is the conditional. Therefore, we mix that one. And here also we use conditional.
Okay, understood. Now, you have shown your sample size from 30 to 500, and for all the value of 5 parameters, all the MLA, etc., are more or less same. More or less same. Isn't it?
No. And not exactly more sense. Approximately is the same.
Then you know, example we have taken 87 students of college wide. You are showing parameter 32, sample size 32, 500. But there you are showing only 87. What was the need of 500?
I will take another examples.
Okay.
Okay, sir.
Banu,
No questions, sir. We have already asked.
comparison table. Uh, we find out the that's why we find out the comparing with the other existent distributions.
No, it doesn't mean that you will always reject the null hypothesis, right?
Yes, yes.
Always.
Yes.
So your rejection region will be very vast. The top is much of your uh, sample space, right? Okay, right. Thank you. Thank you for.
I have a question. In the list, in the name Dr. Biru Satya is not there.
Veer Sukya, sir. Actually,
The list name is not there.
no, no, sir. Bhanot Veerana, sir.
Bhanuri.
Bhanot Veerana.
Veerana, sir.
Bhanot Veerana.
Okay. Okay.
Bhanot Veerana.
Ah,
Actually, this email ID is created for the first my email ID, sir. My 20 years back. Thank you, sir. Thank you so much.
This is the next speaker, Dr. Shamshad Razu.
Yes, sir. Present, sir. Am I audible, sir?
Yes. Dr. Bhanat Veerana, please mute your mic. Dr. Shamshad Razu, please start.
Yes, yes. I'm sharing a screen. Is my visible? Is it visible, sir?
No, please.
Yes, submit, sir.
Shamshad Razu.
Yes, yes. Is my screen visible, sir?
No, all this time is your time. Your time started.
Yes, sir. I'm trying to share my screen. Is this visible, sir? Now?
No.
Can I just join once again? That I'm trying to sir.
ഏത് മെയിൽ? ഇല്ല. അടുത്ത ആടെ ഇത് ചാടിക്കറി. ആ എന്തിനാ തുടങ്ങിയല്ലോ
assumption is that you have taken relay distribution with one parameter. Then generalize it for two parameters. Then we have taken power relay distribution.
No, no, sir. No, sir. What I did is, sir, I generalized the power relay distribution. Okay, sir, without adding an actual parameter. See, power relay distribution was given by homogeneity. I have compared our model with the power relay.
If wherever you have circular type of data, then only one can use the sine, cos, etc. in our program. But there is no case of the supply distribution here. So how we are using the power relay distribution? This is my question. It is also the data.
Sir, what I have do, sir, I have, there was a power relay distribution, I have extended the power relay distribution.
Yes, but this is only used when your data is from the circular type data. But there is no circular type.
No,
Accounting or finance professional. US you are using AIC, all the parametric distribution. For this, you are using example, test set, totally non-parametric.
no, sir, what we are saying, we are saying the difference between the fitting model and the estimated model. We are checking also that one, sir.
Okay, your time is not there.
Well, okay, Dr. Banu, Professor Banu. Okay. Dr. Adel Ahmed, you discussed about the enhanced Rayleigh distribution, but already there is an exponentiated Rayleigh distribution. This is a more general version of the Rayleigh distribution, right? Exponentiated Rayleigh distribution, raising the exponentiated. In what way this enhanced Rayleigh distribution differs from that exponentiated Rayleigh distribution? In what way that overcomes the difficulties of the exponentiated Rayleigh distribution? Of course, enhanced exponentiated Rayleigh distribution has some difficulties for applications.
What the researchers are doing, what the researchers are doing, sir, researchers want to the flexibility of models. Okay, sir.
The thing is, you are discussing the Rayleigh distribution and the theory.
I'm telling sir on that question. The exponential was given the solution, but here also the generalized version of the Rayleigh distribution. One author has given the alpha power Rayleigh distributions. Other has given the Marshall or the alpha power relay. What the researchers are doing, they are giving flexibility in the modeling. If you have to model the to a real life examples, situations, what we need the flexibility. And we are given the models in which we have flexibility. And everyone, when we are extend the distributions, we are comparing it with the baseline distributions. And what I
Not, I could not get the answer. However, okay, right? The thing is, well, if you are given a data set, how will you identify whether the data set receives the applications of enhanced Rayleigh distribution? How will you identify? How will you identify whether you have the applications of enhanced Rayleigh distribution for a given data set?
we are comparing with the baseline models, sir, which are already in the literature. If the value, the minimum of the criterion and maximum value of p value, then we are saying that it fits the best. Our model fits the best as compared to the competing models or this data set. If they have, if they fit, if it fits the criterion.
Now the thing is,
We need some technical answers for this question that identified because it is for the practitioners or for the application purpose. If you have a data set in real life situations, the question is when will you look for the application of your result of that data set? That is the question. If you see, sir, the distribution is widely using the reliability analysis, survival, and engineering. We are taking the data sets for these domains. Okay, sir. What we are doing, we are deriving new we are new deriving new models so that it gives the best accurate values when we are fitting the model in any situation. Okay, right. Thank you, Adil. Thank you for your presentation. Congratulations. Now you can close your screen. And now, Shams Abrazo, are you ready to for presentation? Yes, sir. I already said my TV to station. Mr. Satish Kumar, sir, the organizers. Yes, no, sir. Yes, no, sir. So, yeah, please presentation. Okay. Yes, sir. Thank you. Okay. Can I make it full screen if it's possible, sir? Okay, sir, no issue. Is the screen is visible? Yes, sir. Thank you so much, sir, for the assistance. Thank you so much. Good evening to the junior members, the professors, research scholars from various departments throughout the country. I feel myself lucky and thanking to the Department of Statistics, Kerala, for evaluating my paper and getting selected for the second round. Anti-International Conference. Previously, I have also attended the same conference for which I was shortlisted for the best paper presentation award. And unfortunately, I couldn't figure on the second round. But this time, I hope things will go well in my favor. And hello, 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 hello. Sir, Satish Kumar, sir. Sir, are you on the line? Yes. Yeah, the screen.
ഈ സ്പേസ് ബാർ എനിക്ക് മൈക്കോളാം വേണമെങ്കിൽ Very good. സെക്കൻഡ് സ്ലൈഡ് എടുക്കണം. എടുത്തിട്ടാ സെക്കൻഡ് ഗ്രാഫ് സർവൈവൽ ആണെങ്കിൽ ഓക്കെ പറയാം. ഹസാർഡ് ആണെങ്കിൽ മ്യൂട്ട്. അമ്മയ്ക്ക് മരുന്ന് മേടിച്ചു.
100 into 1 minus epsilon observations from normal 0, p and 100 epsilon observations from normal 5 u, p. The results are given below. All the robust methods can identify outliers, but the false when moving into false detection rate, our proposed method attains the least false detection rate compared to OGK, LCD, and RMDS. Breakdown value. The breakdown value of an outlier detection method represents the maximum proportion of the contaminant data it can tolerate while still accurately identifying outliers. To identify the breakdown value of the SGK method, the study followed by approach suggestions Srinivasan and Kabinaita. We consider the two types of contamination, symmetric contamination and asymmetric contamination. In the symmetric contaminations, each observation is multiplied by 100 into I. On asymmetric contaminations, we have replaced 100 I into U. The simulation results of breakdown value is given for up to 0.45. Our proposed methods are attains a 100% success rate and the 0% false detection rate for the asymmetric and asymmetric data. The computation time of SGK methods are given. To explore the efficacy of the outline detection method in real world scenario, we utilize the benchmark data set, bushfire data by Campbell. This data set has 38 observation satellite measurements on 5 frequency bands. The Marone and Yohai detected the observations 7 and 11 and 37 to 11, 32 to 2 and 38 as an outlier. Our proposed methods are able to identify those outliers. SGK QN based on QN, SGK SN, SGK MAD. We consider the real life data from our Crime in India report 2022. The data contains 18 variables and the 36 observations, which includes 28 states and 8 union territories. This is the data. Our proposed method SGK method identified 4, 5, 8, 12, 13, 19 as an outlier. This is the method in the right corner dot represents a classical method outlier detection. It identifies 8 and 33, 36. We can clearly see that the classical method are highly affected by outliers. Conclusions. The effectiveness of the SGK method was evaluated across various data scenarios, including correlated and uncorrelated data generating from multivariate normal, T, and exponential distribution. The SGK method consistently demonstrated a high success rate in identifying contaminated observations and maintained a significantly lower false detection rate compared to all well-known methods, even in challenged settings such as high-dimensional, low sample size scenarios. Real-world validation further confirmed its effectiveness, successfully identifying outliers in benchmark datasets with low computational cost. These are all important paper I have referred. Thank you.
Vijayalakshmi, for making a presentation in time. Of course, as far as the presentation is concerned, you have proposed a new method, that is SGK method for identifying outliers. And
Yes,
it seems that you have used the mixture distribution for modeling the data containing the outliers, right?
Yes, sir. For generating a simulation study, we have using the for the
For real cases in real situations, when you identify the outliers which are more in number, if it is less in number, right? If they are more in number, you cannot discard all the observations. Otherwise, you will be at the loss of information. You will have to use the mixture distribution, particularly finite mixture distribution specifically.
yes. In this case, our proposed method has even though it is affected by outliers, it can be tolerate 30% of outliers.
It means that the proportion of outliers in the data set is 30%.
30%.
Your parent population will be mixed with two distributions. One will have the mixing proportion of 0.3, other one will have the 0.7, right? It is a conventional procedure. It is a conventional procedure of fitting a finite mixture distribution for a given data. No question of outliers.
Sir, I'm not dealing with the mixture of distribution because if suppose if one observation is taking from F1 distribution.
Now, when you are talking about in the view of you are presenting in the view of identification of outliers.
Yes,
But
sir.
in more general,
when the number of outliers is large, then they cannot be called as outliers, isn't it? It's a data it is a data coming from a population which is heterogeneous in nature, consisting two or more homogeneous populations, which is well represented by a finite mixed distribution. It is a conventional procedure. Yes, sir. We can deal with the using the mixed type distribution also, but now it is enough to plot the display enough to plot the data and identify whether the data comes from a heterogeneous population or not. That's it, right? Okay, now over to other juries, Professor Ghosh and Professor Banu. Uh, so Vijayalakshmi, you said very few time left only because your contents in regards of theoretical parts are very less and application was not good. Now my question is that you have taken a matrix P is equal to some matrix P1, 0, 0, P2, and P1 matrix you have taken highly correlated data, well 0.95, 0.95, and for the another P2 you have taken very negatively low correlated data, minus 0.42, 42, 42, and then from that we are making a P matrix. Is it justified? It is already compared. It is highly, one is a highly positive correlated, one is very low negative correlated, but there is very required of the outliers. Outliers is shown here. So P matrix is the combination of P1 and P2. Yes. Uh, we are taking the worst case for identifying the for the coordinated data. We are taking the worst case of outlier what is it, included in the data. That cannot be compared. At one side, we are taking the highly positively correlated data, and other matrix were taking a very low negatively correlated data. To compare is already made. Outlier is shown already here. No, sir. It is a combination of P1 and P2. It is a six-dimensional matrix, which are there. What do you mean by positive semi-definite estimator? Sometimes it may have a determinant as to be tends to see. Sometimes not done, so we cannot use positive semi-definite. But it not sometimes it doesn't question arise. It need not be a positive semi-definite always, sir. When the dimension is high, it need not be semi-definite always. That's why we are adapting this procedure. And one surprise I am saying, for outlier, for Bihar, it is only 4. In crime rate, Bihar outlier 4 cannot show Bihar. It is real data. With Kerala, you are showing crime only. I'm not able to understand that. What is it? For crime rate data and outliers for Bihar, you are showing 4, and for Kerala, it is 12. Crime rate. The data shows you are telling that part. What does it say? It's happening. And research is about your supply. Understand. From the real life data, I plot that one. Yes, 4 is shows as an outlier. It means it has a high crime rate in Bihar. It shows a high crime rate in Bihar. So, remember your last question. You have used Sinkel's method of estimator, and in the same time we have the lasso estimator. This lasso estimator, it is estimating the parameter up to 0, true completely 0. Compare the Sinkel estimator, but we are using Sinkel estimator. So could you repeat them? Your voice is breaking. Could you repeat, please, sir? Your voice is breaking. We have two types of estimator, Sinkel estimator and lasso estimator. See, when we estimate, then the for lasso estimator, for different value of lambda, that is a minus lambda I, that estimator is decreasing up to complete 0. But whereas in Sinkel method of estimator, it is not absolute 0, it is some nearer to approximate to 0. So that's estimated compared to the that's what we have a condition for minimizing the expected quadratic loss for determining lambda and mu. Okay, thank you. Okay. Professor Banu. Vijayalakshmi, you mentioned in one of your slides that your method works well not only for large data sets but also for small data sets. Yes, the sample size is small. Yes, ma'am. Can you justify that? How you can identify multiple outliers in small data? I do the simulation study for the sample size with the 100. For the dimension 200, 500, I didn't include this one. Our proposed method attains 100% success rate in all the cases, and MCD method has failed because that method is not working for the small sample with a high dimensional data. We done this, but I didn't include this one. The same pattern we got the result. That's why I didn't include that. Yes, ma'am. But I got the result for all the methods. Okay.
One point I want to make, Dr. Vijayalakshmi, that you have taken the data sets are correlated data sets in some cases, right?
Yes, sir.
And
All cases. All cases.
one thing I want to mention, that if you wish to apply your finite mixture distribution as a probability model to represent the data of consisting of, to your different sets of data on set, right? And it is one of the theoretical property of a finite mixture distribution is the component distributions are linearly independent. They are not dependent. They shall not be dependent. Otherwise, it will not at all be a finite. There will be an identification problem otherwise. Right. Okay, right. Thank you, Dr. Vijayalakshmi, for giving more time for interaction. Congratulations. Now, the next speaker, last speaker of this day, Dr. Dhanisri Tanuja.
Yes, sir.
Please share your screen and start presentation.
Okay, sir. Sir, is my screen visible, sir?
Visible.
Okay, sir. Respected to all, good evening everyone. Myself Dhansri Tanuja, research scholar under the supervision of Dr. Sivaji from the Department of Mathematics, Vidyapi University. Here I would like to present my research work entitled with AUC estimation in ROC analysis with non-normal measurement errors and exponential approach. This is the outline of my research work. Section 1 contains introduction, Section 2 discusses the methodology, Section 3 is the numerical support for my research work. Section 4 contains the summary of my entire work and concludes with some references. Coming to the introduction, classification means organizing the data into categories based on their similarities and their characteristics. But coming into the medical diagnosis, the most common classification task is to categorizing the individuals into two classes, with or without given a disease. For example, let us consider a binary classification of two populations. One is healthy and another one is disease. Here P indicates the cutoff value. By using this cutoff value, we can classify the individuals into any one of the two populations. Here TN and TP represents the true negative and true positive, which are correctly classified because the individual who does have a disease is classified as disease and the individual who doesn't have a disease is classified as healthy. But the actual problem is here FN and FP, which are wrongly classified because the individual who does have a disease is classified as healthy, that is considered as false positive, and the individual who doesn't have a disease is classified as disease, that is false negative. To address this such misclassification in biomedical, we generally use receiver operating characteristic curve. That is, it is a plot of true positive rate and false positive rate. The mathematical notation of true positive rate is probability of individual score S is greater than the cutoff value T. Then the individual is considered as disease, and the actually individual rate probability of individual score S is greater than the cutoff value T. The individual is considered as healthy, but the individual actually comes from the disease population. It is misclassified. By using these two intrinsic measures, we can obtain the ROC function as ROC of T. Here G and F denotes the any baseline distribution. For example, if we take two populations follows a normal distribution, then it is considered as a binormal ROC curve.